Hey, it's me, Destin. Welcome back to Smarter Every Day. I love analog film photography. There's something to me about being able to capture a memory in a physical object with light and physics and chemistry. It's just beautiful. In a previous episode of Smarter Every Day, we went down to Montgomery, Alabama to visit Indie Film Lab. These are the people that develop my film, and we got to learn all about the chemistry and the process. It's really, really cool, and I really enjoyed it. But today we're gonna do something completely different. I don't know if you were aware of this, but analog photography is making a huge comeback. It's not just weirdos like Destin that like this stuff. Everybody is trying this. And if you don't believe me, go look up the secondhand prices for old analog cameras like this. They are through the roof, which brings up a question. If analog film photography is popular and analog film is a consumable, what does that mean for the supply of film? Are they just selling some big stockpile, or are they actually manufacturing this stuff today in a way that we can bank on for the foreseeable future? So I'm happy to report that the people at Indie Film Lab introduced me to someone at Kodak, and I asked if I could come see the manufacturing process, and they said yes. Yes, that means we're going to get to go to the place for all things film, the Kodak Plant in Rochester, New York, and I am so incredibly excited. Just to be clear, there's no Kodak sponsorship going on here. I just asked if I could go see the stuff, and they said yes. And I kept asking more questions, and they kept opening more doors. We got to go to the basement to see like the big cauldron, I guess you call it, where they mix the chemicals. This is an incredible few videos because it is going to take 3 videos because of how complicated this process is. There are 3 primary manufacturing things that have to happen in order to make this 35mm can of film happen. Number 1 is the support. That's what I think of when I think of film. That floppy part there, that right there is called the support, and there's a whole manufacturing process that we're going to learn about that goes into that. The second thing we're going to learn about is the light sensitivity part, and that's putting an emulsion over the top of that support and making the film light sensitive. That's its own thing, and spoiler alert, that has laminar flow in the process, so you know I'm going to love that. Number 3 is the packaging of the film. Now, here's the thing to think about. Once you've made the film light sensitive, how do you get it into a package? Because you can't expose it to light after that. So everything from the moment you coat it to the moment it's in the can has to be done in the dark. And we're gonna learn all about that. So there's gonna be 3 videos here. Number 1, we're gonna learn about the support. Number 2, we're gonna learn about the light sensitivity. Number 3, we're gonna learn about the packaging, and I love it. So I hope you're ready to go on this ride because I'm excited. Let's go to Rochester, New York and learn how Kodak makes film for film photography. Let's go get smarter every day. All right, we're going into the lot at Kodak. See if Matt's here. We are at the gated lot.
It says call received when lit, but it's not lit yet.
This is my buddy Trent. When I found out I was going to go to the Kodak plant in New York, I asked him to come along because he introduced me to film and I knew it was something he would really enjoy.
Come on, Matt. We need to see how the magic's made, dude.
hit the help button again.
You Matt?
Yeah. It's Matt.
Yeah.
Nice to meet you, man.
Nice to meet you too.
Pleasure, how are you? So we walked into the iconic Kodak Center in downtown Rochester, New York, and this place is amazing. Our point of contact at Kodak is Matt Stoffel. We geared up, and you know the tour is starting off right when you brush by the world's first digital camera on your way to see the awesome stuff.
We'll definitely come back through here.
Sounds great. What's your title here?
So I'm actually a manager in our worldwide information system, so IT.
Oh, awesome.
Yeah.
Are you a photographer as well?
I am a photographer. I'm a 3rd generation Kodaker as well.
Really?
That's what we call ourselves here. My father, my grandfather, plenty of aunts and uncles, my grandmother. So yeah, it's not an uncommon story here in Rochester.
Yeah?
Wait for the click and then push.
That was kind of a moment. Trent, are you excited?
Oh yeah. I barely fit in this thing.
This is building 1 next to us. Kodak Park originated in 1891.
Okay.
The first building that was built here, if you're going to build a major manufacturing facility, you need some power. So this is a steam generation plant.
It's a really pretty park. This place was absolutely massive, and I was surprised to find out that photographic film is only a small percentage of their business. There's a ton of history here as well. The old brickwork makes it really photogenic, like tons of pipes and textures and windows. It's really cool to take pictures here and just explore the place. We moved along and Matt picked up our ride for the tour, and we made our way across campus to where they make the mechanical support for the film. It was here that we met the experts, Sharon and Mark. Okay, so we are in S-Star film-based manufacturing, and Sharon, Mark, what is S-Star?
Well, S-Star is a Kodak's trade name for PET-based polyethylene terephthalate, and that's polyester, all right, simply. And it's the film base that we use to make a lot of our photographic products these days. There's another base called acetate, but a lot of it's done on S-Star. And we have a continuous biaxial orienting process that we stretch it in 2 dimensions, and that gives the polyester base its toughness. That's why it's real strong.
Oh, so it's a polymer.
It's a polymer, yes.
What's the advantages? Do you get more stability with the S-Star?
Yes.
And do you get more longevity?
Recyclable. It's
very tough.
Tough.
Strong.
Strength.
Got it.
But for that reason, some people have problems with using it in a camera because it might break the camera before it.
It's too strong.
Oh, the tensile strength is higher.
Yeah,
Yes.
much higher. So acetate is it tears very easy, and therefore motion picture film still, at least origination film, is still on acetate.
Because you want the film to fail before the camera fails. So it's a mechanical strain relief in the system.
Right.
Correct.
Got it. Okay.
However, if you're in a projector, that thing's going through and you've shown that movie, you know, however many hundreds of times while it's sitting there in the theater.
You gotta wear it out.
That strength there so that it doesn't wear out.
Got it. Understood. Sharon and Mark gave us a detailed rundown of how all this stuff works, and after only a few minutes, it became clear to me that they are geniuses. But it's that fun, humble, wizard-like genius that's earned through many decades of solving complex problems. They knew the speeds, the mass flow rates, the temperatures for everything. There's a lot to learn here, but I hope that at the end of this tour, you have a fundamental understanding of every major part of the S-Star film support manufacturing process. While Trent and I are suiting up here, there's one more thing I want you to be on the lookout for on our tour. There's this theme that I saw everywhere I went at Kodak. It's clear to me that there's this group of wiser, more experienced employees, and they're taking the time to gradually bring the younger folks up to speed. Not only that, but you can feel the excitement of the younger generation as they actually own it. Like they're watching what's going on, they're taking that knowledge and that understanding, but they're also getting the work ethic from the older generation because they're seeing it being modeled. Keep an eye out for this in these videos because it is impressive to see this young tech-savvy generation absolutely kicking butt because of their work ethic, and you've got the older generation cheering them on, saying, hey, I know I designed this machine, but it's yours now. This is your legacy, and they're putting them out there. They're like, hey, you should be the one on camera. It's really cool to see this partnership between these two generations because it absolutely encourages me about the future of American manufacturing, and it gets me really excited. Charles, you've been here 2.5 years?
Yes, sir.
So he's an old timer.
Oh, yeah. Seasoned veteran.
One of our veterans.
Yes.
All right. Yeah, you mind telling me about the polymer?
Yeah, so this is just polyethylene terephthalate pellets. So we get it in from our current supplier.
Okay.
So we get it in this pelletized form and we end up converting it into a powder. Our whole process is built on using a powder because we used the larger surface area during the solid stating. So since everything was already set up for that, we like to keep it that way. It also helps when we add in our stabilizer later down the line that we can...
I'm going to put this in your hand.
Yeah, okay, that's fine. So that'll help us out, get the stabilizer mixed in as well, because you really can't add it to the pellets. Again, surface area is really important. And that keeps the inclusions down on the machine, keeps our film really clean optic.
What was that word?
Inclusions?
For air inside.
Not air, but just for defects. The stabilizer is actually for taking out catalyst residue. If you leave it in, you get some nasty looking freckles in the background.
Got it.
And you just can't have it on the high quality optical film.
So if I understand correctly, this is where film starts.
Yes.
Got it. So we're going to grind it, make the surface area where we can melt it easily. We're going to melt it down, then we're going to extrude it.
And then it'll get extruded out through the die into the wheel.
That's awesome. Yeah, let's check it out. So Charles explained that they bring these pellets in on railway cars. They have their own tracks on campus, and they pull the rail car up to the building, and one car of pellets will last for 2 days. The first step in the process is to mechanically grind up these relatively large pellets into a fine powder. Charles took us down to see the grinders in action.
They're 250 horsepower motors.
Yeah.
They'll grind out about 10,000 pounds an hour max.
Uh-huh.
You have to take a peek inside.
Yeah. That's our powder. That's the powder.
Yep.
So that's the powder that's going to start the whole process to make the backing for the film. So that's a polymer powder,
Yes.
polyethylene.
Yep, that's a polyethylene terephthalate powder.
Okay.
So coming in from the top, we have a pneumatic conveyor. Dilute phase picks up all the powder from the bottom of the grinders, and it transplants it upstairs to our roof. So it's going about, I don't know, 100 feet up.
Oh, that's awesome.
Into a 300,000 pound storage tank.
It's amazing. Really cool elevators.
Yeah, very old elevators.
It's awesome. The next step we're going to learn about is what Kodak calls the reactors.
So we're just going to walk through the control room.
Okay.
Al, how you doing?
What's up, man?
This is Al, our best operator.
What's up,
Hey,
Al?
Chris.
How's it going, man? I'm Destin.
All right.
Doing all right?
Yeah.
You guys making it happen?
Trying to.
Trying to?
Oh, you taking pictures?
Yeah.
Yeah.
So this is where you control everything.
Yeah, everything's controlled from here. We have pneumatic panels on the wall, so we still have some of the very old original pneumatic stuff. These are 5 of our reactors, basically. The older ones are all controlled from this panel pneumatically. And you basically can see just about everything that's going on and keep track of it. This is the fluidized polymer reactor, so this is where we would do the solid stating.
So you're drying
So
it.
at this point, right now we're drying it. Yeah, it's down to 5 parts per million of moisture, or water by weight, so it's pretty dry.
Where can you read the moisture here?
So we actually do that using an IV in our lab. Every batch we'll take a sample, and then we'll run it through one of our Tinius Olsons, look at the intrinsic viscosity, and then we correlate that with the moisture.
Intrinsic viscosity meaning when it's melted?
Yeah, so we put it through like a Tinius Olson. It's a little machine. You put your sample in, and it's basically a tiny extruder. And then it just measures the forces and gives you that viscosity.
Oh, that's awesome. Yep, that's cool.
Yep.
And you can correlate that to moisture?
Yes. Based on the water content, it'll have a different IV.
IV?
Intrinsic viscosity.
Got it.
So it's basically the amount of water or solvent in the polymer. So these are some of the older FPRs we have. I'm only bringing it in here because I want you to just be able to take a look.
IPRs, what do you mean by that?
FPRs, fluidized polymer reactor.
Uh-huh.
The only reason I brought you in here is this one's out of service, but it gives you a really good shot of the inside. So this is how it fills, gravity fed from the top. What it will do is it will feed from up above all the way till it plugs that line. When that line is plugged, you can't fill it anymore. So that's when our batch is ready to be put into react mode. At
So
the bottom,
basically you have a pipe coming down.
yes,
So that goes way up high.
yes.
You have the pipe coming down, and when it's full up
All
to
the way to the pipe, that's when our batch is ready. Now these are about 10,000 pounds worth.
and this will be dry powder at this point.
Going in, it's wet. It's going to be dry and ready when we're done with it. Ready for stabilizer edition, that is.
Got it.
At the bottom, those coils, those are the internal heating coils. We also have some external heating coils wrapped around on the jacketed vessel. Those bring us up to temperature.
Gotcha.
Yep.
So basically, wet powder comes in, meaning like it has too much moisture.
Correct.
Goes in here. These coils down here.
They provide the heat source. So what's going on is it's a fluidized bed reactor.
So air's pumping in.
So nitrogen, because everything has to be nitrogen.
Dry
inverted.
nitrogen.
Yep, so dry nitrogen flows in through the bottom. There's a distribution plate with tiny holes in it, and that keeps the powder moving. It's kind of like an ocean. You see waves and ripples and bursts as it's reacting. It's pretty cool.
That is cool. Yeah, so do you guys monitor it with cameras or something?
No, I wish.
Yeah.
We usually just have sight glasses with lights.
So is this under pressure? Why?
The whole vessel will usually be under pressure, yeah.
Really?
Yes, around 7 PSI or so.
Oh, that's legit.
Yep. So these are all 10,000 pound reactors. And then over here, we have 2 20,000 pound reactors that we run all the time.
So these are running?
Yes, they're currently running. So they each have a compressor that just recirculates the gas. They have a glycol scrubber associated with it to help strip the nitrogen through our adsorbers. Again, you want to keep your nitrogen clean. Organics will come off during the process, acetaldehyde and some other compounds.
So do you just vent the nitrogen?
Nope, it's clean and it's recirced. We try to conserve as much as possible. Just about every conveyor we have here is closed loop because nitrogen is expensive.
Yeah, that makes sense. Is all this stainless?
Yeah, everything's stainless steel. Anything that touches the resin has to be stainless steel.
Stainless steel?
No aluminum allowed, no silicon.
Because it could oxidize.
The aluminum is bad for the product inclusions. If it gets in there, any aluminum dust, it's a big issue.
How's he doing, Sharon?
He's great.
He's doing great?
He's great.
Yeah.
So coming out of these FPRs, it is conveyed up to the right above us. There's another bin, and then we put everything through this screener. It's just a big corn sifter.
Yeah.
And its entire purpose is to get anything large that might be in the process out. Make sure we only have good polyester coming out the bottom.
A uniform size.
Yes.
This controls your grain size.
Well, somewhat. I mean, there's just about everything helps control the size, but this will get anything large out. If there's a wall scale like we saw in the last reactor, there's those large on the outside edge where you get the amorphous material, all that'll come out of here.
Got it.
Now, of course, the whole powder has a distribution associated with it. We check that in our lab checks because we like to keep the particle size
Like a standard
pretty
deviation.
uniform. Yeah, for the most part. We have an acceptable range.
So that's the end of your vision into the process.
Well, there's a little bit more upstairs, but yes, basically I'm done
the
with
first
anything.
stage.
Yes, correct. So we give them the finished powder, so that way they can go straight into the extrusion and then the film making process.
Oh, that's awesome. Charles, nice to meet you.
Nice to meet you.
So the next step of the process is the initial melt screw, and I didn't understand this at first, but it's very interesting. Mark took me to the feed hopper on the floor above the screw and showed me where they could add color to the material by feeding in colored pellets if they wanted to. We then went down to the basement and suddenly everything got very warm and very loud. That's a big motor.
Yeah.
Is that a gearbox?
Gearbox, a few hundred horsepower, lots of heat, lots of noise.
Okay.
So this is the feed hopper, gravity feeding the powder and the ground reuse into the feed throat area of the screw. And then the screw's turning, accepts the powder, and that gets pushed along through, generates so much frictional heat that it melts. I will take you to, we have a screw that's out of the machine.
Let's do it.
Sitting on a cart. I can show you that.
So it's rotating very fast.
No, it's not actually. About 30 RPM.
Oh, okay.
Something like that. Yeah, it's going pretty slow. And we've got all the piping is jacketed because the melt temperature is around 540 degrees Fahrenheit. So we're trying to control everything to uniform temperature. The screw's a little ways down here, so we got.
Mark, you just barely make it under these things.
Yeah, yeah.
Are these calibrated for Mark's height? Is that what we did here?
Close.
That's a gearbox right there.
Gearbox, yep. Couple of spare parts.
These are huge. Oh wow. This is amazing.
This is the screw. So this is the
This is an auger. This is incredible. I cannot, the key stock required to make this thing work.
This is a big project to make one of these. There's a barrel, and then this gets installed in the barrel, and it floats in the barrel. Yeah, it has to be very uniform in temperature because you don't want any warping.
How tall are you, Mark, for scale?
6'5".
6'5". Wow, so that's like 6 Marks. It's like 40 feet.
Yeah.
Like 10 Sharons.
Like 10 Sharons.
So these are the different stages of the screw. You can see where the flights.
It's called a flight?
It's deep here. Yeah, the flights of the screw. It's deep here, and then it gets shallow. So you build up a lot of pressure in here.
Oh.
You know, as this material it's flowing through here, a lot of pressure, and all of a sudden it goes down in pressure, and we actually pull a vacuum through this little hole right here.
So this doesn't rotate?
It rotates. This is rotating all the way around, but the material is only up to about here. It's being pushed along by these flights, so this is open area, and this screw is actually hollow. There's a pipe that goes through it. We pull a vacuum on it.
Oh, I see. What is that
continuously.
for?
It gets rid of volatile gases.
Oh,
It's,
I see.
Icky stuff, you know.
So that the face of that gets sealed on the outside? That's hard for me to understand.
Well, not the base of this doesn't get sealed, but the flights are pretty well sealed
Okay.
in the barrel of the screw.
Okay, so you, and that just seals on the other end, right?
Yes, it seals on the other end.
Okay, so let me understand the process. So we put the powder in here.
Right.
There's a pipe that's a set diameter.
Yep. All around this.
And so that seals right here on the edge.
Right.
So this powder starts here. Does it come in here?
It comes in there.
Right here.
Right there.
So once it comes in here, it pushes the powder that way. This is like an Archimedes screw on steroids kind of, but it's not using gravity for liquid. So as mass comes in here, it starts moving that way. You've got a gap here.
Right.
And as you go down, the gap gets smaller and smaller. So you're way over here. And you can, there's a really big step right here.
You're building pressure here in here.
And then it gets very thin. So the gap gets very small here. And then why do you relieve the pressure right here?
So that we can have this vacuum area where we pull a vacuum on it and extract. It's called the extraction section. So we pull a vacuum and extract volatile gases from the little bubbles and things like that.
And then it keeps going?
Then it keeps going, and then it pressurizes again. And our pressures coming out of the screw are like 1,200 pounds, 1,200 psi.
Wow.
You know, it's 400 or 540 degrees.
And so when it comes out on this side right here, oh, look at that. What am I looking at? Does this ride in something?
Yeah, I think there's a place that it kind of floats in on the end.
Kind of like a needle bearing.
But the material actually takes a turn. Let's see, we're downstairs. So we go upstairs through a filter and then through another screw. So there's two screws actually. This one does the heavy lifting. Melting, pumping, pressurizing.
So this, you can see it really good here. So comes down, off gases, recompresses.
Recompresses, right.
So it's converging, diverging, converging.
Yeah.
Yep.
Okay, got it. Is this an extra one?
It's probably a box. We got several
There's
extra
an
ones.
extra one there.
Yeah.
Oh, this is an extra one.
Look at that. Didn't even know you had that, Mark.
Looks like it needs to be cleaned up.
We got all kinds of.
It's got a sign on it that says "Save this screw."
Does it really? Lou Haresta wants us to
yeah.
save the screw.
Her Lou is our extrusion engineer.
So can we go back to the motor?
We can.
This is crazy.
Just to show you what this is a scrap chopper too. So we don't have these upstairs, but as we go through different parts of the machine, there are little gates in the floor. We send scrap down, and this is where it ends up. So they could chop it up into little pieces, and then we sell it.
Gotcha. So now that we understand the screw, this is our motor and our gearbox, and the screw is in here.
Right.
And the hopper, the material's coming in there,
Material's coming in.
and it's compressing all the way down. Where's the vacuum? It's in the middle, right?
Yeah, it's actually pulled. The vacuum's in the middle. There's a pipe
Yeah.
that they put in. You see, there's the end of the screw.
This is the end of the screw.
The resin is flowing up.
This is the resin coming
resin
out.
flows up.
Okay, you may already have this figured out, but I'm clearly still confused, so I need a visual aid to help me figure this out. Here's the rotating screw, and up top you can see a cross-section view of that same screw. The shape here is exaggerated, by the way. That'll make everything a little bit easier for us to understand. The material comes in the top here as a solid powder, and friction alone heats it up and melts it. As the molten material gets pushed down the length of the screw, it gets compressed between the shaft and the sidewall. The shaft then reduces in diameter, which relieves that pressure a bit, and a void opens up, allowing the material to outgas. A vacuum is then pulled at this little vacuum port, and unwanted gases can bubble out and be removed. The screw then continues to push the uniformly molten polymer to the end, where it exits out the top. This is the screw running at 42 RPM.
42 RPM, yeah. At 4,400 pounds an hour.
That's the rate of the material leaving.
Without reuse, but with reuse it's 35. So if we didn't have that recycle loop in there, it would be higher.
When Mark told me they filter the output of that screw, I found that to be hard to believe. They do, and it's impressive.
I'll show you the filters. Oh, you can't see too much, but there's a canister. There's a canister with, so the resin gets pumped through a set of filter sticks. So we've got usually 10 micron or 5 micron filters, depending on which.
You're filtering
product.
the plastic?
Yeah, we're pumping that resin through a set of filters.
You're pumping the resin through a filter. What?
Yeah, we don't have any good pictures of filter sticks, but it's a fine mesh.
So these are one-time use filters then?
No,
we break them down and clean them. And
Stainless steel mesh.
Wow.
We pump through.
That's amazing. This is one of the most interesting parts of the process to me because I've never thought about filtering a molten polymer, but of course that's a thing. But I've never thought about that. That looks like a mess. You clean this thing.
yeah, they break it down here and then it goes up to our filter cleaning room.
So you guys are the kids that mess things up and you got somebody else that cleans up after you.
Yeah, that's
got
pretty
it.
much it.
That's amazing.
It's fun. This is the other screw that I talked about.
Oh, there's 2 screws.
It's a little smaller. Yeah, it goes, so we were downstairs, comes upstairs, there's a filter on the other side of the wall. At high pressure goes through the filtration step, comes over to this screw. This is called the metering screw. So this one is a lot smaller and it doesn't have all those flights where we go high and low. So it's just pumping material. So like the name says, metering, if we want to increase the thickness a little bit, we speed this up. If we want to, thin it out, we slow it down.
This is the fine adjustment.
Fine adjustment. And again, the one downstairs is doing all the heavy lifting, all the work. So all that surge, if there's any surge, pressure fluctuations, this one's keeping all of that stuff away from the process, the casting process.
Got it. This episode of Smarter Every Day is sponsored by Brilliant. Brilliant is a really cool app and website that you can use to learn really cool science concepts at your own pace. Brilliant offers a ton of courses focusing on mathematics, science, computer science, and more so that you can learn all these really interesting concepts and move from knowledge to understanding. This episode, for example, is about photography. Let's say you wanted to get a more scientific understanding of photography, so where would you start? You just whip out the app here, go to Brilliant, start looking around. I just found one called Waves and Light. You can just start the course and it goes through all different kinds of interactive tutorials about what is a wave, how does it work? And then they have interactive questions that you can respond and get feedback on whether you're actually understanding the concepts. If you want to check this out for yourself, go to brilliant.org/smartereveryday. That gets you a free membership and 20% off a premium membership. You begin to master a subject when you have the tools you need to figure the answers out on your own. And that's what Brilliant does. It helps you master a subject. Brilliant offers a wide range of courses from mathematical fundamentals to quantitative finance, scientific thinking, even special relativity. If you want it, it's there. Go to brilliant.org/smartereveryday to sign up for free, and that also gets you 20% off an annual premium membership. Big thanks to Brilliant for supporting Smarter Every Day, and thank you for considering supporting the sponsor. This looks like you guys are walking to like your rocket or something. Up until this point, we've been processing the material to get it into the perfect molten form. Now it's time to go upstairs and watch it take shape. All right, so the molten stuff comes up, right?
Comes up after it goes through 2 sets of filters. There's a final filter and it comes through the wall, filters on the other side. And right here at the 12 o'clock position of this wheel is a die.
So we've got the melted PET, the plastic, and we're going to turn it into film. So we've got this big wheel here, right?
Right.
And is this where the molten plastic comes on top of the wheel?
Yeah, right at 12 o'clock, coming out of the die.
All right.
It's being extruded. You can picture it's very viscous, very thick. And as the wheel turns, it's picking that up. And in order to get it to stick to the wheel, we pull a vacuum behind that. So it makes it stick to the wheel and makes it even all the way across.
So this wheel that's rotating is very, very, how do you say this? The surface finish is almost like a mirror.
Polished.
Polished?
It's a polished surface.
Polished surface.
And it's cooled.
Okay, so you're maintaining the temperature of it too.
Right.
So you've got the molten stuff coming in the top. It goes all the way around, and you keep a vacuum on it. So are there holes in the surface of the wheel?
No.
No. So there's only a vacuum right here.
Okay.
Once we get it attached to the wheel, it goes around.
It stays.
So liquid goes there, and it goes around this position all the way around.
All the way around.
Down the basement.
Down the basement where we saw earlier. Up here.
It cools to a certain point.
Okay.
540 degrees coming out of the die, liquid. And by the time it gets to this point right here, it's about 135 degrees Fahrenheit.
Gotcha.
Because the wheel is cool.
Got it.
And as quickly, it's important too how quickly we cool everything. If you cool too slow, you get a hazy crystalline structure. So you have to kind of have controlled cooling to do that.
So it's kind of like when you take your ice cream out of the freezer and put it back in. If it cools slowly over time, you'll get big crystals. But if you cool it quickly, you don't get crystals.
That's kind of the way it is, yeah.
Yeah.
And you do that for optical clarity.
Okay.
You want this to be as clear as possible.
Okay, and so we create the film and then we pull it off of the wheel.
Yep.
Right?
And it's pretty thick at this point.
Yeah.
It's very thick. It's like a board.
What we showed you in the conference room.
So it's moving pretty slow at this point, but it's very thick. It's like 1/8 of an inch.
Right.
Yeah? And then where do we go from there?
So it goes through, these are drive rollers, pinch rollers. We're just conveying it. And
So it's coming down, going up, down, and then back here.
back here. And we got a cooling section. There's a temperature control area in here. These are our coating stations.
Kodak was very proud of the fact that they can apply coatings to the material as it travels along the production line. They introduced me to another young engineer named Patrick who explained how they prepare these coatings for application at various steps along the process. They have an entire system set up to precisely measure and get the right temperatures. It's very complicated. I asked Mark and Sharon why you would coat the product, and there were a ton of different applications for this process. They said you might want to put a primer on the S-star so that the photosensitive layer would bind better. You might have an anti-static layer, you might have a conductive layer. They said you might even put gelatin over the top, and it varies depending on what the final use of the product is. One room I thought was really cool is where they store all the combustible solvents. This room is literally fortified for explosions, and the solvents are stored in containers that are electrically grounded to prevent a static discharge from starting a fire. It felt like a really serious room. Perfectly preparing these chemical coatings is very important, and the way they're applied is a very precise operation. So I'm looking through a film base right now. I'm 1, 2, 3 layers.
Correct.
But it's very thick.
It's a very thick material, and you get thick, very thick edges. We call those ribs.
Uh-huh.
And those are going to be important for us to grab hold of so we can stretch.
Gotcha.
Ultimately.
So you're grabbing the ribs.
Grabbing the ribs.
And so it's going up there.
Goes up. If we were coating, we'd be drying the sheet upstairs. All right. And once we've dried it, both applications, we're ready to start stretch.
So it's going from the wheel there, it's going over, and then it's going down and up there, back down.
Right.
So it's kind of zigzagging back and forth.
Yep.
And then we get here, and this is where we would coat. Well, we coat there as well.
There and there.
Got it.
Face side, back side.
Gotcha. And then what?
Well, once we're done drying this last coating, we're ready to stretch.
The next part of the process is called drafting and tentering. Drafting is actually stretching the material in the direction of travel, and tentering is stretching it out to the sides.
A lot of people ask the question, why do you have to stretch it? Why can't you just extrude it? And so the process of PET and some other polymers, the molecules are very long and they're not oriented when you cast. So this process gives them orientation, and that's what makes it very tough.
So up to this point right here it's going that way. Up to this point, it's the same diameter, it's the same width and thickness.
Right.
So our mass flow is always the same throughout the entire process.
Right.
So when you start stretching it, you're going to squish it,
Going to squish it. It's going to thin down
and then it's going to speed up.
and speed up.
Yeah.
So how do you know how much to speed up your rollers?
Oh, there's no drive rollers in here. So in this whole section, the sheet doesn't touch any rollers. So between
Pinch
here
the edges.
and
Just
there,
the ribs.
Yeah, it holds on to the ribs, and that's where we get our structure, or that's where it holds the sheet.
Gotcha.
And we overspeed down there to stretch it.
Is that the bulk of what we're going to chip back up for the regenerative part? Is from the ribs?
Yeah.
Yes. Not yet though. We need those ribs.
We need them to stretch in both dimensions.
Gotcha. So this is like pulling a bubble in a. Okay, I'm got you.
Like taffy. You're going to stretch
Yeah.
taffy.
It's just like taffy.
I'm heating it up, and all this is just heat transfer error. All right, and we're going to heat it up, and I'm pulling on it on that end, a lot of tension, and as soon as it gets up to a certain temperature, uniform temperature all the way across, it's going to stretch just like taffy will. And we have to hold on to those edges because just like taffy, it's going to want to neck in and thin down. So we're grabbing onto those edges
With a roller.
and that's what these are. There's edge rollers.
Is it possible to see one of those?
Well, not while we're
running.
while we're running.
Cool.
But you could see the gap starts thick, and right here it's being gapped. It's stretching in here, starting here, going down tighter and tighter. So the stretch point is right in here.
What are you telling me to look at when you say see the
See
gap?
these gaps, these numbers
Oh, I see.
are going down. So we're at 107.
Oh, 100.
Here's
That's the thickness of the material.
thickness of material,
In inches,
thousands.
thousandths of an inch.
Thousandths of an
107
inch.
thousandths,
You see it's getting thinner.
97 thousandths. Oh wow, big steps.
Yeah.
50 thousandths of an inch.
There's a lot happening right in here. And we're gapped on the end to keep it from necking in.
Gotcha. So it's speeding up right here.
It's speeding up in here.
Really fast.
Really fast, yep.
So from 100 thousandths to 50 thousandths, we've doubled our speed right here.
More than doubled. It's about, our ratio is usually around 3.5.
Got it.
Have to,
What is this? Sure.
those are those rollers.
Little
that
roller
grab
you
the
were
edges.
asking about.
That's how you're grabbing the edge. Can I touch it?
Sure.
So that's what you're grabbing on. Wow.
It's called a drafter bar.
It's got just a little bit of a taper on it, doesn't it?
Yeah, because of those ribs. It's trying to form contact with the ribs, so it doesn't dig in.
Gotcha. That's cool.
This is a cooling section. We cool the sheet. There's no stretching going on in here because then we're going to hit some of these full face rollers to transport it from here into the next step. So there's a roller in here that we have under high tension. This is the tension roll. It means we're pulling very hard, and that's what causes the stretch to happen
Got it.
when it gets up to a certain temperature.
Gotcha.
Dave?
Yeah, because you can't push it. You got to pull it.
Right.
Got it.
So,
That's interesting. So the tension is pulling through the stretch.
right.
That's weird.
And the stretch point, if I pull harder, I can move that stretch point around. So it's pretty important to keep that tension where it is and keep that amount of heat that's going in there to be a relatively constant, because that keeps those rollers. It's always going to want to stretch in the same place.
That's straight up crazy. You're pulling taffy and you're controlling where it stretches.
Pretty much.
So the speed is passive. There are no rollers. I got it. I'm with you. What are we doing here?
So we're getting ready to stretch it in the other dimension.
Lift.
Tentering. Tentering. Okay.
Might call it machine direction is back there. This is direct
Lateral
direction, or cross web. You can't see it, but there are two very long chains that one's on this side and one's on the other side. All right, and the chain is just rotating, going round and round, and you can see there's things that we call clips, and there's almost 1,000 of them. That's a clip counter. The numbers will go up to like 980, and then they'll turn over. But the clips are attached to the chain, and as the sheet comes into the clips.
It grabs it and it moves.
We have a cam that knocks the clips closed and locks onto the edges. And as we're going to do the same thing in the tenter here, we're going to heat up the sheet and it's going to stretch it, diverge out. Those clips are going to diverge out and widen out and stretch the sheet in the
How do you
widthwise
keep
direction.
the film from stretching in the middle more than the outsides?
Yeah, you have to heat it up uniformly. So that heat transfer in there is important in how we do that.
So you guys are wizards.
Yeah,
Sharon,
exactly.
you're a wizard. You right?
Well, he's a wizard. Mark's a wizard.
Okay.
No, a lot of
Gotcha.
other people are. So you can see here we're about 16.5 inches wide, this number right here. And we're just, through this section, we're just adding heat.
Tenter. So we're adding heat at this point.
Adding heat, still 16.5.
16.5 inches wide. We're gonna walk down here. Okay, we
A little bit wider.
added 1/8 of an inch.
Yeah, not much. We're just basically trying to keep tension on there. Whoa, all of a sudden we're at 38 inches.
Wow.
So we've had a lot of stretch happen in here.
What's happening here?
It's 60 inches, so we're full width. That's our full width.
So
here on
from
out.
there to there, you stretched it width-wise, all it's gonna stretch.
Right. Once it's stretched, we take it up to a higher temperature. It's called a heat set. And we have to lock that structure, that molecular structure. We stretched it two ways, so you got molecules now, instead of being kind of intertwined like spaghetti, you know, is all mixed up. And we take it up to a higher temperature and we lock that crystalline structure in. You have molecules that are lined up lengthwise and widthwise, and that's that tough PET property that you get. And then we're going to cool it down once we get up.
And so it's shrinking in dimension because
It's actually, yeah,
contracting because of thermal properties.
because of the thermal properties. And we also, when we release over here, we don't want it to be too tight. We don't want a lot of tension on there, otherwise we'll throw chips and stuff like that. So we let it relax just a little bit.
Oh, it's a lot bigger.
Yeah, you can see it's a lot wider. And we still have that thick rib out on each edge.
Okay.
But we're releasing these clips, and this chain with the clips on it just heads on back to the other end and just continuously rotating around, opening and closing clips.
That's amazing. Oh, no way. This is their goodbye ribs.
Goodbye ribs, that's
And
right.
that's the material we recycle and reuse.
So this is where we cut the ribs off.
Right.
And so that's awesome.
And then we reuse that material that goes right back into the.
I felt emotionally attached to the ribs at this point. It's pretty neat.
They served us well, though.
Yeah, they did.
So is this an X-ray?
Yeah, it's a nuclear device.
What?
It's a radioactive.
You just hand waved a nuclear device, Mark.
Yeah, it's safe. Trust me.
If you don't open it, you're good.
No, that's amazing. Okay, so
So you might be able to see it better here.
this is measuring the thickness.
Yes, it's measuring its thickness, non-contact, and it's feeding back to the die. We've got some heaters back at the die that will tell, from the information that gets here, tell it to, I need a little more material here, or I need a little less material over here.
Okay, so this is feedback all the way to the beginning of the process.
Feedback all the way back to the beginning.
To that die
to that
that
die.
you saw on the wheel.
Really?
So that's a very sophisticated piece of equipment. That's very.
Okay, so this deserves a pause. So here we are. We're after stretching. We're after tentering. We're after cooling. We're after cutting the ribs. So this part of the process, way down here, minutes later, this is feeding back all the way to the beginning and telling that die how to roll molten material on the wheel. Am I
Right.
getting that right?
You are getting that right.
Really?
And there's a banks of heaters in that die, and they adjust the heat to, as feedback from the thickness. So it'll adjust the heat to get the right thickness.
So that's a major part of this process.
Yes, it is.
You laughing at me, Sharon?
It's cute. It's very cute.
This is awesome. So at this point, the material is this wide and they have the ability to send it off to do several different operations. The material is sent upstairs where Mark showed me a coating station where they can apply a coating to the full width of the product. You'll understand this concept better in the next video. There's a huge dryer they can then send it through, and then it comes back downstairs where a bunch more operations are available. They can knurl or emboss the edges, which apparently Sharon owns several patents for. They can also slit the film up to different widths if they need to.
There's a scanner in here too where we have where we look for defects. So that's part of this, and then we wind up the roll.
Can you show me where it winds up at the end?
Oh, yeah. Oh, yeah.
This is our scanner. So a lot of this is little spots and little defects. The scanner sees things. There's a laser and some CCD cameras that are inspecting the sheet.
That's amazing. So these are defects.
Those are little things that the scanner saw. Those are very small, and we have limits on how many of those.
These are feet.
That's feet.
Oh, okay, so this is huge.
It's a map, and that's widthwise location.
So is it rolling? Is this?
It's rolling.
So it's scrolling to the right, correct?
It should be updating.
Got it. The final step in the production process is to roll up the product, but in order to do that, you must first use something called an accumulator. When a roll gets full and you cut the product to change it out for a new roll, because the process never stops, you'd end up making a huge mess in the time it takes to connect a new roll. To solve this problem, engineers came up with a clever arrangement of rollers that can be spread apart to magically buy workers a few precious seconds. Okay, this accumulator concept is amazing, so it's hands-on learning time. Check this out. So this is the setup, and it looks pretty simple, but it's very, very complicated. This is a motor controller, and we're going to feed the material into the product line right here with this can at a constant velocity. Over here, you can see we have what's called the accumulator. It's a series of pulleys cleverly arranged. And on this far side here, we have a take-up spool. And the thing about the take-up spool is I can vary the velocity that it is operating at, okay? So this is how we're gonna do it, and I'm gonna show you all the different things that come into play because it is fascinating. So we're gonna cut on the motor controller over here, and we're gonna start playing, okay? Let me get my spool going in the right direction. Okay, ready? So I'm gonna turn on the thing, and when I turn this on, we are going to feed the line through the entire setup at a constant velocity. Everything is working, right? So constant velocity here, I have good tension here, good tension all through the system. If at any time I want to stop spinning there, I have to take up that extra distance in the line by pulling on the accumulator and spreading it apart. Now see, I still have good tension here, but I'm no longer moving. So I could change my spool out here or whatever it is I want to do. And let's say we change the spool and we have a new one on there. And at this point, I want to keep my tension over there so I could start taking it up again, and then I could let the accumulator go back down. It's doing it on its own. Isn't this awesome? It's going back down, and we are maintaining a constant velocity here, but at the same time, we're spooling it faster over here. One thing I want to point out is while the accumulator is moving, you can see because it's stationary over there, you can see that string on the right is not moving, but on the left, it's moving fast because it's still the constant velocity of the production line. That's fascinating. And I gotta move my hand over here and start taking it back up. Isn't that amazing? Yeah, so this is cool. I had no idea how this worked at first, but it's impressive and amazing. And maybe we should go back to an animation. Okay. Think of it like a constantly balancing equation. The velocity of the production at the beginning of the line must equal the velocity of the accumulator plus the velocity of the spool at the end of the line. Having an accumulator in the system gives you the ability to slow down and stop the product whenever you need to make a cut and start a new spool. The accumulator was a very difficult thing to film because it was so huge and spanned several floors of the building, but there was a smaller version up towards the front of the line that gives you an idea of what the setup is like. All right, it's time to roll up the product. I'm Destin. Destin?
Destin?
Yeah.
Good to meet you, Steve.
Steve, nice to meet you. I'm Destin.
Bill.
Bill, what's up? Nice to meet you, Bill. So this is the final product here.
This is the final product. So they'll be cutting a roll here pretty soon.
This is our current speed right now.
Coming right off.
Yep.
260 feet per minute.
Yeah.
So you're at 5,500 feet. So we're gonna back up and let you do your thing.
Well, that's okay. You still got time. So what we watch here is we watch our take up, and that's very important. So when that comes to a stop, that's the accumulator taken up, and that tells us how much time we have. So I'll cut the roll. By the time I walk out of there, we'll probably be at about 41%. Okay.
And you take pride with keeping that number as small as possible?
Oh yeah. Oh yeah. Oh yes.
Because that's your margin for safety on the process. So you're 5,680. What's about to happen?
Well, it's going to start slowing down. Probably about 57. Probably about 57:20. Your red light's going to go on. Around there. Yeah.
Okay. Yeah. And so you had that label ready. So this is the product.
Now we're coming to a stop. So the red light went on. Now you keep an eye on this here. Right now the accumulator is slowing down right now.
So you cut it with a knife.
Yes, sir.
Cut that section out. You're starting a new one.
That first cut right there is our sample.
So what's your accumulator percentage now?
31%.
That's because you're so good at what you do, right?
Do our best.
Is that a good number?
I probably could have got 25.
So right now our accumulator is coming down now because the accumulator is closing back up. So you'll watch our speed here too. You see how our speed actually increased? So now that speed will start working its way back down to the 365, 368.
Really?
Yes.
That's exit line on the accumulator?
Yes.
So the accumulator...
So the accumulator is just, it's coming in fast. Well, the accumulator is opening up, but yet it's slowing it down for us to be able to make our cut. And then it has to catch back up to speed, so it's going to keep going. It's going to stay fast and then come down as it's coming back down. Your speed is going to start lowering back to MSP speed.
So ultimately, the line never changes its speed.
No.
But you have to be at 0 speed when you make that cut.
Yes.
And so the accumulator buys you a few seconds to do that, and then you got to spin back up fast, and then the accumulator backs it off for you.
Yep.
All right.
Back to speed.
All right, so now what do? Now you got a full thing there.
Now what we'll do is, we've already taken our one quality sample. Depending on what our dimension sheet calls, or our test schedule sheet calls for, we will take our appropriate samples that we need.
Are you the quality man?
For the bench. He's our quality guy.
Okay.
Some products require a third sample, which is called a keeping sample. And this is a sample that is kept upstairs in stock in case the engineers need to review the sample, or if something was found by the customer that has a complaint or something, they can say, hey, can you look at this product for, say, this roll? And they'll go back and see, maybe for instance they had a scratch and we didn't see it, but they had a scratch and they recorded, hey, we saw a scratch in one of our rolls that we bought from you. And we'll go back and look. What they do from there, I'm not sure, because I'm not part of that. But
this is your domain here.
Yeah, but they use the keeping samples as a reference.
Tell me about your knife, Steve.
It's the famous knife that's always been used from the beginning. Our Cutco knives. This is probably it's probably my 5th or 6th blade, because by the time you start sharpening them, they start to dull out and then they start to wear down.
5th or 6th blade. How many years have you worked here, Steve?
In this building, about 21, 22.
Are you telling me 20-something years you've had 5 knives?
Yeah, yeah.
Really?
Yeah.
Is there a light curtain here?
Yes, there is.
So don't go forward. Got it.
It is right here.
Safety curtain line. Got it.
Right now, the light is green, so we were able to go in here, but you can still see how it works.
Gotcha.
When this light is red, that's like a no-go. You will not go across there, and if you end up going across there, it stops the wind-up.
Steve, it was awesome meeting you, man.
Yes.
Thank you. So how are you going to get that roll off?
I'm going to just pick it up and throw it on my shoulder and bring it out.
Is that what this bad boy is?
All right. So each card is set for a certain size of the core too. So you want to make sure that it fits on there, and you don't want to make sure that your core falls off.
How do you release the spindle?
What I'll do is right now we're up. So you stay right there, you stay right there. There's a button back here. So this button back here, I will lower this, all right? I'll lower that so it sits in the cradle.
Oh, you rotate the whole thing.
My other guy here, he'll help me. We guided it together, so we're working together. So I'm reaching back, he's pushing in, I'm pushing in, and then we have over here to your right.
Yep.
There's a chuck, so I'm on A core right now, and you'll watch when I press the A core button.
Oh, it's a cone. Got it.
That releases, and it releases over here also, because these are torque. These are a different kind of a torque. Gudgeon, so
that's got a logo
sides,
on it, yeah.
Yeah, both sides have to be taken out. So I'm gonna swing out, so you just guys don't want to get hit.
Yes, sir.
And then that gets taken out to what we call the roll room, and it gets packed.
You like working here?
Engineers, oh man, I love working here. I love working, period.
I can tell.
I gotta be crazy, but yeah, I love working here.
So after this entire roll is manufactured and scanned for quality, it can then be packaged in what's called a casket. These are large wooden devices that they use to ship this product around and protect it. From there, it can be used for many different things. It might be sent to a different building here at Kodak where it's turned into photographic film, or it might be used to manufacture electronics. It might even be sold to an external customer and it's shipped out to a different location. Did you enjoy that? I really enjoyed the tour of the Kodak plant in Rochester, New York. Remember, this is the first of 3 videos. And so at the end of a video, there's typically like a call to action, you know, subscribe or whatever. We're not gonna do that today. This is all I ask of you. Please consider going and finding an old film camera. It could be like in grandma's drawer. It could be like at the thrift store, at a yard sale. Find an old camera and breathe new life into it and put a roll of film in that thing and go out and just be creative. It's cool because it's like, it's for you. It's not for the internet. You get to make a film photo and it's yours and it's really cool. So I hope you'll check that out. Also, there's 2 more videos here. So this was making the support. We've still got to put the light sensitive layer on there, the emulsion, and we've got to cut that up and we've got to put it in the little film canisters. And it's really, really exciting. Thank you for watching Smarter Every Day. I'm grateful for your time. I know you have a billion other things you could watch on the internet, but you're spending time here with me doing stuff that I find interesting, and I'm grateful for that. That's it. Thank you to everybody that supports on Patreon. I'm grateful for that as well. I'm Destin. You're getting smarter every day. Have a good one. Bye.